This is a demonstration of a beam bridge, and this is probably the hardest bit you'll have about moments of a force. We've got a couple of supports of a bridge, and I've put them on balances so you can see the forces. Here is our beam bridge, just made of a couple of metre rulers. And if I get it roughly central, then you can see that we have about the same weight showing, same mass showing on each of these, and therefore the same weight, the same force pushing down. Now it's slightly smaller there, 121 compared to 124, so if I adjust it ever so slightly, it should even it up a bit. 1, 2, 3, 1, 2, 3. And the whole reason is that if I put things off centre, then the centre of my bridge, which is at the 50 centimetre mark, because it's a 1 metre rule, if we consider that all the weight is here, well, it's nearer to this one. So there's much more weight at this end than there is at that end. So I'll try and even it up. You will notice though, no matter how much I move it around, these two numbers, wherever I put them, will always add up to the same. So I've got 116, round up to 117, 129. Yeah? So if you add those up, that's the same as if I prop it right on the end, and they will add up to the value of the full thing, which is 242-ish. I'm balancing it in my hand, but about 142 grams. 242 grams. So the total force down will always be the same because it's just the weight of the bridge, and it doesn't matter where it is, where it's slid along, it'll always be the same weight. However, how it turns is what causes the weight to change. So we have to think about the turning effect, the moments of this bridge. And so if we, as I said, we'll get it slightly more even, 123, 122.8, that's close enough. So we can look at that effect and we can think about it if we think about how a bridge is used. So if we have Bob, who is in this case a 1 kilogram mass, but if Bob walks across the bridge, then of course the bridge has to support him on the supports as well as the actual beam. So both of those go up and they will still give the total of Bob and the bridge. But as we move along, we've got 147 here. If we move it along, 767, 580 roughly, 400, etc. So as Bob moved along, then the weight at this end, the force needed to keep the bridge up at this end, is getting smaller and smaller because Bob is actually putting more of his weight on that end of the bridge. So that is getting heavier at this end because that's where most of the weight is. Okay, so most of the classic questions about this are fairly straightforward if you're thinking about where Bob is. However, you've got to remember the weight of the beam as well, because that beam has weight and that will be evenly spread usually in the questions you get. But even if it's an advanced question, it still adds up to the same weight. So if we take the idea here, why is it causing more weight at this end than it is at this end? Well, if you think about what it was doing without Bob, you were just lifting it up. Okay, the two supports, these two forces that we're measuring, effectively multiply that by G in kilograms, so 0.853 times 9.81, that would get the actual size of the force that is being pushed on here, which of course is equal to the force pushing up against the beam. Okay, so we've got Newton's third law here, you're pressing down on this, it's pressing back up, they're in equilibrium, same amount in both directions. However, what we've got is, if we think about the pivots, if we treat this as a pivot, we can work out all the forces involved just by looking at this end. Okay, so if I push down harder on here, actually on the pivot, it's not going to change those results. Yeah, and I will get something to demonstrate that now. I'll do my best to, if I get it exactly on, so 393, I'll push harder on here, it's still 393.7. It's gone up 1/10 of a gram there. So it's not changed much. So basically you can ignore the forces here by assuming everything here acts as the pivot and everything else is just being pushed on this end. So what we've got here is this beam, the support is pushing up at this point, and it's pushing up with enough force to equal out the weight of the bridge pushing down and this weight pushing down here. So to do the mathematics, we need to consider the moments. We take the distance from the pivot. So here we've got around about 25 centimetres, and you've got basically 10 newtons at this point, 1 kilogram times by G, basically 10 newtons at this point, pushing down. If this bridge was to snap, it would tilt round, so it's tilting round the pivot in a clockwise direction. The weight of the bridge is also trying to push it around this pivot point. So this moment, force times that distance, plus the weight force times that distance will equal the moment in the other direction. So the force here multiplied by this bigger distance. So in terms of the mathematics, much bigger distance, so that's a much smaller force. And if we turn it around and move it somewhere else, then again we can do it. That's got bigger because that force and distance hasn't changed for the weight of the bridge, but the force times the bigger distance for Bob means that I need a bigger force times distance pushing back, pushing anti-clockwise. Okay, so if you're having a little bit of struggle visualizing it, just imagine the bridge snapping, but not falling off, just actually tied down there. Both the two halves of the bridge would tilt round. Okay, so you're trying to think of it as a turning force, even though it doesn't look like anything's turning because it's nice and flat and in equilibrium. Okay, but that's the only way to explain how the numbers change as things move along. Now, if you wanted to do the maths on the other end, find out how strong this is, then again, it's in the book, it's in the notes, but we could do the moments treating that as the pivot and working back. Okay, so force times that distance, etc., or we could just remember that both of these add up vertically to the total vertical weight down. Okay, and that's just much easier. So the weight of that plus the weight of that equal those two added together. Okay, and that's how to treat beams and other such turning forces. Anything where forces change, equilibrium is not just up and down, left and right, it's also forces turning around.